2 videos ago, we saw how we could construct a line from the vertex of an arbitrary triangle down to the opposite edge, such that it meets that edge at a right angle. We then saw how we could calculate the length of that line using trigonometry. In this video, we're going to apply the same concept to prove a very useful relationship between angles and edges in an arbitrary triangle. This relationship is known as the sine rule. By defining relationships between edges and angles in arbitrary triangles, this rule is incredibly powerful because it allows us, if we know certain combinations of angles and edges, to find other angles or other edges in any triangle. So let's start out by drawing an arbitrary triangle here on the whiteboard. So I don't know, how about something like this? So a nice arbitrary triangle. And I'm going to name the edges and angles in this triangle. Now there's something important here with the sine rule when we're dealing with our naming convention. I'm going to use lowercase letters for edges, and I'm going to use capital letters for angles. It doesn't matter which edge of the triangle gets named with which letter. So in this case I'm going to say this edge is A, this edge is B, and this edge is C. It doesn't matter which edge gets named with which letter. However, when we then name the angles, we need to name the angle based on the edge that they're opposite. So if I was naming this particular angle here, I'm going to name it based on the fact that it is opposite the edge A, and so I'm going to name it capital A. This angle here is opposite the edge B, so I'm going to name it capital B. And this angle here is opposite the edge C, so I'm going to name it capital C. So our lowercase letters are for edges, our capital letters are for angles. It doesn't matter which edge gets which letter, or I guess which angle gets which letter, as long as the angle-edge pair, where an angle is opposite an edge, have the same letter, only the angle is capital and the edge is lowercase. So once again, capital A is opposite lowercase a, capital B opposite lowercase b, capital C opposite lowercase c. The lowercase letters are edges, the capital letters are angles. So now that we've got that out of the way, let's take an approach like when we were finding the angle of an arbitrary triangle, and let's break this triangle into 2 right-angled triangles. Now in this case, I'm going to do this by dropping a line down from capital C down to our lowercase c, such that it meets C at a right angle. That's going to break our triangle into 2 right-angled triangles, and it's going to give us a new edge in both of those triangles, which we can call H, as it kind of represents the height of our triangle. It also creates a new point. I'm going to name this new point capital D, and we can see that the 2 right-angled triangles that we've formed, if you will, form the triangle ACD and BCD. Now, by using trigonometry in each of these right-angled triangles, we can calculate the length of H. If we look at H in terms of what we know, well, we don't know the length of this edge or the length of this edge because we've just split an edge that we possibly knew into 2 arbitrary portions, and we don't know the length of those. We don't know the angle up here or this angle here because again we've split a known angle into 2 parts and we don't know the proportions of those parts. That means in ACD what we know is A and B, and in BCD what we know is B and A. So how are we going to find the length of H using trigonometry in both of these triangles? Well, in ACD we know if A is the angle that we know, H is opposite that angle, and B is opposite our right angle. So B is our hypotenuse. So we're dealing with the opposite and the hypotenuse. That's related with sine of the angle. So sine of the angle is equal to opposite over hypotenuse. So in ACD, that means sine of angle A is equal to H divided by B. We can rearrange this to find H. So H is equal to sine of angle A multiplied by B. This is more commonly written as B sine A. Fantastic. So that is our right angled triangle ACD. Let's now take a look at BCD. So again, we're finding the length of H, but in this case, it's sine of B is going to be equal to the opposite, which is H, over the hypotenuse, which is A. So in our other triangle, we have sine of B is equal to H over A. That means, of course, that H is equal to sine of B times A, which is equal to A sine B. So both B sine A and A sine B are equal to H, and that means they're equal to each other. So I can now say that B sine A is equal to A sine B. If we divide both sides by, I don't know, let's pick on sine of A to begin with, that means that B is equal to A sine B over sine of A. And then if we divide both sides by the sine of B, we get B over sine of B is equal to A over sine of A. Fantastic. So we're already getting a useful relationship building between edges and angles in an arbitrary triangle. So let's create another line in our triangle. In this case, the line that I want to create, instead of going from C to C, I want to create a line from B to B. So I need to get rid of this line. So I will actually delete that layer. And I do need to erase some of the extra parts that we added to our diagram. Fantastic. So I'm going to create a line that goes from B to B, and it needs to join B at a right angle. So it's joining B at a right angle. Now, in order to differentiate this from our earlier diagram, I'm going to call this line H2 rather than H, and the point of intersection is going to be E rather than D. But we're going to have similar relationships here. We again have two right-angled triangles. This time we have ABE and BCE. And again, using those right-angled triangles and using trigonometry, we can find the length of H2 in terms of known components. So looking at ABE, we can see that the sine of A is going to be equal to the opposite, H2 over the hypotenuse, C. So if I was to scroll down, I'm going to have to squeeze this in so we don't run out of room, but we know the sine of A is equal to H2 over C. That means that H2 is equal to C sine of A. In our other right-angled triangle here, we can see that the sine of C is equal to the opposite, H2 over the hypotenuse, A. So sine of C is equal to H2 over A. That means H2 is equal to A sine C. Again, H2 is equal to H2. They are the same. That means we can make these two parts equal to one another. So that means C sine of A is equal to A sine of C. If we divide both sides by sine of A, we get C is equal to A sine C over the sine of A. And then if we divide both sides by the sine of C, we get C over sine of C is equal to A over the sine of A. And we've already seen that A over the sine of A is equal to B over the sine of B. So that allows us to say that A over the sine of A, well, we've seen that's equal to B over the sine of B. We've also just seen it's equal to C over the sine of C. Fantastic. This, right here, A over sine of A is equal to B over sine of B is equal to C over the sine of C. This is the sine rule. All you need to remember is that the ratio of an edge divided by the sine of the angle opposite that edge is equal to the same ratio for the other edge-angle pairs in any arbitrary triangle. Now there's actually a little bit more proof that we need to show to fully prove the sine rule, and that's because there's another case of arbitrary triangle that results in slightly different calculations, though eventually they do prove that the sine rule still holds true. Now ordinarily I'd avoid overcomplicating things by delving deep into mathematical proofs, since all that really matters is that we understand the rule and we know how to apply it. However, in this case, by showing the proof, we're going to get to practice using trigonometry, and that's no bad thing. The more we practice using trigonometry, the more comfortable we're going to be with trigonometry. So in this case, I am making an exception, and I am going to show the full proof. So if we think back to our arbitrary triangle, we can see that we define this arbitrary triangle, we drew it on the whiteboard, but there's actually another type of arbitrary triangle, another case of arbitrary triangle that may have cropped up. So if I erase everything we've done so far, hide that out, and create a new layer, we could have had an arbitrary triangle that looks more like this and less like our original triangle. The significance of it looking like this will become apparent shortly. So I'm going to name our triangle much like we did our original triangle. So the naming convention, of course, is that the lowercase letters are edges, the uppercase letters are angles, and that the letters that are the same but just a different case are opposite each other. So angle A is opposite edge A, and so on. Now you'll notice with this triangle, and this is why the shape of this triangle is significant, that if we followed the same first step that we did with our original triangle to create a line from point C, angle C, down to edge C, such that it meets at a right angle, you'll notice inside the triangle we can't meet at a right angle. There is no physical way, due to the positioning of the vertices of this triangle, that we can meet at a right angle. Now in this case, that means the only way we can meet at a right angle is if we extended C outside of our triangle and dropped our line down right around here. So we could have extended C outside the triangle and dropped a line down. Now we can name this much in the same way that we named our original triangle. So D for the new point, H for this edge, but the significance is because this new edge doesn't exist inside the original triangle, it's outside the triangle, our two right-angled triangles are now slightly different to before. We have a large right-angled triangle, ACD, and we have a smaller right-angled triangle, BCD. Again, we can use trigonometry and apply it to those right-angled triangles to find H, but we're going to see that our calculations are just slightly different to before. So let's pick on our large triangle first, our ACD triangle, and let's apply trigonometry to find H. Now again, we saw that sine of an angle is equal to the opposite over the hypotenuse. So if we said our angle was A, well then the sine of A is going to be equal to the opposite, H, over the hypotenuse B. So sine of A is equal to the opposite, which is H, over the hypotenuse, which is B. Therefore, H is equal to B sine A. So in the case of our larger triangle, if we remember H is equal to B sine A, if we looked back to our earlier calculations, we can see here H is equal to B sine A. We actually get the same result. So our larger triangle is not an issue. However, let's look at what happens with our smaller right-angled triangle, and you're going to see that actually things work a little bit differently from before. So again, we need the sine of theta is equal to the opposite over the hypotenuse. Well, the opposite edge is going to be H, the hypotenuse is A, but notice the angle we're trying to find, theta. We don't have this angle. We have this angle here, we know this angle is B, but we don't have theta, or do we? This is a straight line, therefore theta is equal to 180 degrees minus B. We can see B, we know this entire angle is 180 degrees, therefore this must be 180 degrees minus B. But that means our calculation is slightly different, because now we have the sine of 180 degrees minus B is equal to the opposite, which is H, over our hypotenuse, which is A. If we rearrange this, we get A times the sine of 180 degrees minus B is equal to H. But before, we had A sine of B is equal to H with our original triangle. So notice these aren't the same, they're different. One has 180 degrees minus B, the other simply has B. Was this going to cause us a problem? Actually, no, it's not. Let's take a look at our graph of sine theta to see why. So I'm going to hide out all of these guys, and I'm going to bring up our graph of sine theta. And we actually happen to be positioned perfectly for sine theta. Fantastic. So if we take a look at our graph of sine theta, we're saying that we have one thing was sine of an angle, the other was sine of 180 degrees minus that angle. Well, we know that our angle is not going to be larger than 180 degrees because if it's an interior angle of a triangle, it can't be larger than 180 degrees. So you notice in the range of 0 through 180 degrees, we're symmetrical about 90 degrees. And because of that, it means any angle, the sine of any angle between 0 and 180 degrees is equal to the sine of 180 degrees minus that angle. Because we're symmetrical, however far we move from 0 up, if we move the same distance from 180 down, we get the same value of sine theta. So because of this, it allows us to say that the sine of 180 minus b is the same as the sine of b. So let me delete this new layer with doodlings on, hide out our graph of sine, and then bring up our layers again. Fantastic. So this allows us to say that the sine of 180 minus b is the same as the sine of b, and that means that again, just as before, we now have that h is equal to a sine b. It's also equal to b sine a, and we've seen this is the exact same results as we got with our earlier arbitrary triangle example, so everything will rearrange and prove once again that the sine rule is still the same, that a over sine a equals b over sine b equals c over sine c. But I just wanted to show that extra proof, mainly because we got to practice more trigonometry, and we got to see how understanding the graphs of the trigonometric functions can really help us when we're solving a problem like this. Okay, so before I move on to set you guys some questions of your own, I'd like to work through an example question myself. So let's bring up a new whiteboard. Just hide out everything we've done so far. Bring up a new whiteboard. And I'm going to draw a triangle. So here is a triangle. And let's say we know some of the information about this triangle. We know that this angle here is 20 degrees. This angle is 30 degrees. This edge is 5 units long. And the question I'd like to answer is to find the length of this edge I have just marked with a question mark. So what is the length of that edge? Well, let's recall our sine rule. Our sine rule states that a over the sine of a is equal to b over the sine of b, which is equal to c over the sine of c. So we know that the ratio of an edge divided by the sine of the angle opposite that edge is equal to the same ratio for each of the other edge angle pairs. Now in this case, we can see 20 degrees is opposite our edge that has a length of 5, and 30 degrees is opposite our unknown edge. So we can write this as an equation using part of the sine rule. So we can say that the edge that has a length of 5, well, let's say that that was a, so 5, is equal to the sine of the angle opposite it, so it's equal to the sine of 20 degrees. And that's equal to, well, let's say this edge we're trying to find is x. That's equal to x divided by the sine of 30 degrees. So again, an edge divided by the sine of the angle opposite that edge is equal to any other edge divided by the sine of the angle opposite that edge. So here we have 5 over sine of 20 is equal to x over sine of 30, where x is the length of the side that we're trying to determine. So we can rearrange this quite simply to find the value of x. If we multiply 5 over sine of 20 by sine of 30, by the sine of 30 degrees, that's going to give us x. We've multiplied both sides by the sine of 30. That's cancelled out on this side, giving us x. And it's given us 5 over sine 20 times sine 30 on the left. So we can now calculate this. We can use a calculator to work this out. So here is a scientific calculator. And if we took 5 divided by the sine of 20, so 20 sine, which the sine of 20 is 0.34. If we click equals, that tells us that 5 over the sine of 20 is 14.619. I can then multiply that by the sine of 30, so 30 sine, which is 0.5. If I click equals, it tells us that our edge, x, is approximately 7.31 units long. So x is approximately 7.31 units. And that's all there is to it. It's really easy to use the sine rule. So now that I've worked through a question on my own, it's now your turn. So please note, in case some of you do skip the questions in these videos, there's actually a little bit more theory that's about to be covered as we work through the answers to these questions. So if you usually skip the questions, I highly recommend watching this particular video and the questions in this video all the way through to the end, even if you don't actually attempt the questions yourself, just so that you don't miss out on any of the extra theory that is going to be covered. Alright, so let's look at the first question. I'm going to bring up a new whiteboard so that we have as much room as possible to work here. So starting out, this is question 1. And I'm going to draw a triangle. So something like this. And the information that we know about this triangle is that this angle is 35 degrees. This edge has a length of 5, and this edge has a length of 8. And for this question, I'd like you to use the sine rule to tell me one possible value for the angle that is marked with a question mark. Again, use the sine rule to find one possible value for the angle that is marked with a question mark. Go ahead and pause the video. When we come back, I'm going to work through the answer on the whiteboard and then going to introduce some more theory that relates both to the sine rule and to trigonometry in general. Okay, welcome back. So using our sine rule, which we know is A over sine of A is equal to B over sine of B, which is also equal to C over sine of C, but we don't need to worry about that because we only have two edge angle pairs in our particular problem. So using our sine rule, we can say that 8 over the sine of 35 degrees, since, not 350 degrees, thank you very much, sine of 35 degrees, since 8 is opposite the angle of 35, is equal to 5 over the sine of our unknown angle. And I'm going to call our unknown angle x. Knowing this, we can rearrange to find x. If I multiply both sides by the sine of x, we get sine of x multiplied by 8 over the sine of 35 degrees is equal to 5. If I then divide both sides by 8 over the sine of 35 degrees, we get sine of x is equal to 5 divided by 8 over the sine of 35 degrees. Now, those of you who are familiar with divisions and fractions would know we could simplify this down further, but since all of these are known values, I'm simply going to use a calculator to get the value of the right-hand side, which will tell us the value of sine of our unknown angle. So bringing up a calculator, we're going to take 5 divided by, and I want to divide it by the evaluated value of 8 over sine of 35 degrees. So I'm going to open parentheses to make sure all of this gets evaluated first. 8 divided by the sine of 35 degrees, close parentheses, and then equals. So 5 divided by 8 over sine of 35 degrees tells us that the sine of x is approximately equal to 0.358. So the sine of x is approximately equal to 0.358. Therefore, to find x, we can use our inverse sine function. So x is equal to the inverse sine of 0.358. If we use our calculator, so 0.358 inverse sine, we get that if we were to round this up to the nearest degree, x is approximately equal to 21 degrees. So x is approximately equal to 21 degrees. So that's one possible value. That was the value I was hoping you were going to find just simply using the sine rule. But why, when I set this question, did I mention one possible value? Because this suggests that there's more than one value. But how can this be? Surely there's only one solution to this problem. Well, let's look at the problem more closely. What do we know about this problem? Well, we only know 3 pieces of information: this angle and the length of 2 of the edges. So this problem clearly states that there's an edge that has a length of 5, and connected to that edge is an edge with a length of 8. But we don't know the angle between those two edges. And because we don't know the angle between those two edges, we can think of our edge of length 8 as freely rotating about the point where it connects to our edge of length 5. If we took the end point of that edge and we drew an arc for all of the possible points where that edge could rest with rotating around this endpoint here, we get an arc that looks something like this. Now, of course, it would form a complete circle, but I'm just going to draw part of the arc. And that's as our edge rotates around, it would draw out an arc with its endpoint. Now, we also know that this edge right here connects with an angle of 35 degrees, but we don't know the length of that edge. So that means the edge could be really short, or it could be really long. So to represent this, allow me to draw a dotted line in the direction of that edge. What you'll notice is the information that we have actually allows us to create two different triangles that satisfy that information. The first triangle is a triangle that we had already drawn. Notice the other triangle where our edge and our arc cross over would be something more like this. So we'd have a larger triangle. So this is because the information that we know actually allows two possible triangles to satisfy that information. We simply don't have enough information to rule out either of these triangles. And again, this is because we don't know the length of this particular third edge. If we did, only one of the triangles would be correct, and in those cases, as we'll see in the next video, the cosine rule, not the sine rule, is actually easier to use to find that unknown angle. But in this case, and back to the problem at hand, we have two possible lengths for this edge. In the same way, we have two possible angles here, and two possible angles here, because there are two different triangles. So where in our workings did we go wrong? Where could we have got two possible solutions for the unknown angle? Well, it all comes back to that last step in our workings. We knew that the sine of x is approximately 0.358, and then we use the inverse sine function to calculate an angle given that ratio, given that value of 0.358. But recall, our inverse sine function has a limited range. It will only ever give us one possible angle for an input value. But there are multiple different angles that the sine of that angle is 0.358. And we know that inside of a triangle, any of those angles would have to be between 0 and 180 degrees. But if you think back to when we introduced the inverse sine function and we talked about the graph of sine, even between 0 and 180 degrees, there are two possible angles that give us the same sine of that angle. And we actually saw that in this video when we proved the sine rule for the second type of arbitrary triangle. We said the sine of 180 degrees minus theta is equal to the sine of theta. So therefore, when we calculated the inverse sine of our ratio, our value of 0.358, and that gave us the fact that x is equal to 21 degrees, our angle is equal to 21 degrees, there's actually another angle that would satisfy a sine of the angle being 0.358. And that is the fact that sine of 180 degrees minus 21 degrees is equal to the sine of 21 degrees. So that other angle is 180 minus 21, it's 159 degrees. So x not only equals 21, but it could also be 159 degrees. Now, of course, we're never going to get 159 degrees from our inverse sine, because our inverse sine only ever returns a value in the range of negative 90 to positive 90 degrees. So it would only ever tell us 21 degrees, but there are two possible angles, and we simply, without more information in our problem, we simply do not know which of those two angles is the unknown angle. It could be either of those and still satisfy everything else we know about that triangle. Alright, so keeping that in mind, here's another question for you to attempt to solve. So I'm going to bring up a clean whiteboard. And this is question 2, the final question of this video. And we're going to have a triangle. So let's draw a triangle. And we know some information about this triangle. We know that this angle here is 40 degrees. This edge has a length of 12. This edge has a length of 9. And what I'd like you to do is to tell me the two possible lengths for this unknown side of the triangle. Now this problem is a little trickier than the previous question, but just use the sine rule to find what you can and then work from there. And here's a little tip. The interior angles of a triangle add to 180 degrees. So with that, go ahead and give this an attempt. Once you have a solution, or if you get stuck, unpause the video and I will work through the complete solution here on the whiteboard. Okay, welcome back everyone. So starting out, we can actually use the sine rule to work out this angle here, which I'm going to call x, because we know that 40 is opposite 9, and we have an edge here of length 12, which is opposite this angle. So we can actually use the sine rule to find our angle x. So writing this in the form of our sine rule, we know that 9 over the sine of 40 degrees is equal to 12 over the sine of x. We can rearrange this to find x. So I know therefore that the sine of x multiplied by 9 over sine of 40 is equal to 12, and therefore the sine of x is equal to 12 divided by 9 over the sine of 40 degrees. If I use a calculator now, we get 12 divided by open parentheses 9 divided by the sine of 40, close parentheses, equals, that tells us the sine of x is approximately 0.857, so the sine of x is approximately 0.857. We can now use our inverse sine to get a value for x. So the inverse sine of 0.857 is equal to, if we bring our calculator back up, the inverse sine of that is approximately 58.987 degrees. So 58.987 degrees, which means that x is approximately equal to 58.987 degrees. So we could write that in up here. We could say that this is 58.987 degrees. But we must be careful, however, just as in our previous question, we don't know the length of this third side. And because of that, and because we don't know this angle here, we could have a different value for this angle. We know that because our edge here could rotate. Because it could rotate, there are two possible lengths of this edge which still meet all of the information that we know about our triangle. And we saw earlier, just as in our previous problem, that the sine of 180 degrees minus theta is equal to the sine of theta. That means that x could also be equal to 180 degrees minus 58.987, and that means it could also be equal to, well, let's use a calculator for this, 180 minus 58.987 could also be equal to 121.013 degrees. So 121.013 degrees. So there are two possible values for x. X is either equal to 58.987 or 121.013. Now I'm going to find the answer using this first value of x, and once we have that answer, I'm then going to go back and repeat the solution, but using our second value of x. So using our first value of x, now that we have x, we can actually calculate the third angle in our triangle, because we know that the angles in our triangle add to 180 degrees. So if I called that third angle y, we know that 180 degrees plus, or rather, we know 180 degrees is equal to 40 degrees plus x plus y. So 180 is approximately equal to, since x is an approximate value, y plus 58.987, that was the other value of x that we had up here, plus our other angle that we already knew, which is 40 degrees. So y plus 58.987 plus 40 degrees, which if we rearrange for y, tells us y is approximately equal to 180 minus 58.987 minus 40, which gives us that y is approximately equal to, if I use a calculator, 180 minus 58. Oh, my apologies, let's start again because I pushed the wrong button. 180 minus 58.987 minus 40 is approximately equal to 81.013 degrees. So 81.013 degrees. And again, we could add this to our diagram. So this is 81.013 degrees. Well, if we know this angle, which is opposite the edge we're trying to find, we could take either of the other edge angle pairs and use our sine rule to find the unknown edge. Now I'm actually going to take the edge of length 9 and the angle 40 simply because we only have an approximate value for the angle we've called x. We know the exact value for the angle that is 40 degrees because that was part of the question. It really won't make that much difference to the result, but I personally prefer to use the most accurate results possible whenever I can, and we know the exact value here, whereas this was just an approximate value. So if I have the choice, I'm going to use the exact values that we know. So let's call this unknown edge z, and if we recall our sine rule, we could say that, as I guess I should do it up here very quickly, we could say that y over the sine of z is equal to 9 over the sine of 40 degrees. So if we remember that, y over the sine of z is equal to 9 over the sine of 40 degrees. Oh, wow. That's not our sine rule at all. My apologies, everyone. That's kind of crazy. Z over the sine of y. That's better. Z over the sine of y is equal to 9 over the sine of 40. Again, my apologies. I really hope that didn't confuse anyone. So z, which is an edge, over the sine of the opposite angle, y, is equal to 9 over the sine of 40 degrees. So if I then scroll back down, z over the sine of, and the angle was y, so z over the sine of y, which is 81.013 degrees, is equal to 9 over the sine of 40 degrees. That means that z is equal to 9 over the sine of 40 multiplied by the sine of 81.013 degrees. We can use a calculator to work this out. So 9 divided by the sine of 40 gives us 14. Then we multiply by the sine of 81.013. Gives us z is approximately equal to 13.83. So one of our answers is that z is approximately equal to 13.83. That is our first answer for the length of the unknown side. But what about our second answer? Well, we need to come back to where we had two possible values for our angle of x, and we need to work through the rest of our workings using that value for x. So the first thing we need to do is we need to use our x to work out y. Well, y is equal to 180 minus x minus 40. So in this case, it's equal to 180 minus 121.013 minus 40, which is equal to 18.987. So let me just check again. I just want to make sure I type that in right, because it's not quite what I have in my notes. So minus 58, oh, my apologies, minus 121.013 minus 40, 18.987. Okay, so that's what we're going to go with, if that's what the calculator is telling us. So 18.987. So if x is equal to, or rather y is equal to 18.987 degrees, well, that means that z over the sine of, in this case, 18.987 degrees is equal to 9 over the sine of 40 degrees. That means z is equal to 9 over the sine of 40 times the sine of 18.987 in this case. So again, bringing up a calculator, 9 divided by the sine of 40 degrees is equal to 14 again, multiplied by the sine in this case of 18.987. Which, if we work that out, tells us it's approximately equal to 4.56. So not only is z equal to 13.83, it could also be equal to 4.56. And again, that all comes back to the fact that we don't know two of the angles and we don't know the length of this edge, and because of that there are two possible lengths of this edge that satisfy that problem. So once again, the two possible lengths you're looking for are 13.83 or 4.56. So it is worth mentioning quickly that in the next video we're actually going to see another way to solve the same type of problem, and again it's going to give us two answers, but it doesn't require us to remember that the sine of 180 minus theta is equal to the sine of theta. So you may prefer the method we see in the next video for solving this type of question rather than the ones shown here, but they are both valid. So hopefully the previous two questions have proven just how useful the sine rule and trigonometry in general is for solving problems relating to triangles. So to recap, we use trigonometry to derive a relationship between the angles and edges of an arbitrary triangle. This relationship, known as the sine rule, is A over sine A is equal to B over sine B is equal to C over sine C. Now the key to this relationship being that the ratio created by dividing the length of an edge by the sine of the angle opposite that edge is the same for every edge-angle pair. Now not only is this relationship itself very useful for solving problems relating to triangles, but we've seen that the work we've completed in this video has really helped to demonstrate just how powerful trigonometry in general can be. So with that, that is going to conclude this video. Thanks a lot for watching, everyone.